Hey, what's up? I made a previous video about the Coulomb force, and from the Coulomb force, the notion of an electric field. And so I want to take those ideas and continue to build on them with the concept of electric potential. So just a quick refresher. So when you got two charges, those two charges experience a Coulomb force, and that Coulomb force is proportional to the magnitudes of those charges, and it's inversely proportional to the square of the distance between those charges. So the other thing you need to consider with charges is that you have, when there's one positive and one negative charge, they are attracted to each other. So the Coulomb force is an attractive force. But if they both have the same charge, if they're both positive, if they're both negative, then they're actually going to repel each other. So you have to keep into account the signs of the charges. So Coulomb forces are forces experienced between charges. And you need to consider the sign of the charge, the magnitude of the charge, and how far away the charges are. When you have an inverse association with the square distance, it means that the forces get exponentially stronger the closer and closer the charges are. So with respect to a field then, if you have a single charge, you can draw a field around that charge. And what that field is essentially a hypothetical map where if you brought a second charge into the situation, then you would have a Coulomb force that both of those charges experience. But if you're only dealing with one charge to begin with, it's just a hypothetical map because you don't know where that next charge has been placed yet. So an electric field is this hypothetical map of all the different places that another charge can be placed. And when it is placed there, it would experience a Coulomb force that is equal to whatever the magnitude of the electric field is, multiplied by the charge that you put there. And with physics, there's usually a convention that we talk about test charges when we're talking about these hypothetical maps. So in other words, if I have some charge Q1, I could draw a hypothetical map where if I brought in some test charge, and this is often called Q naught, where it's the Q and there's a little subscript that looks like a little zero. So if I brought in some test charge Q naught, then the Coulomb force that it would experience would be the magnitude of the field due to Q1 at some location multiplied by Q naught placed at that location. So again, this is a hypothetical map based on the presence of Q1, and if I brought some test charge Q naught into the situation, or if I, for instance, have some Q2, well, I will know just based on the hypothetical map that we draw for Q1 that if I put Q2 at some location, then the Coulomb force that would be experienced would be the magnitude of the field at that location. And again, that field is predicated on Q1. So the magnitude of the field at that location multiplied by Q2. So think of the electric field as the force per charge. So in other words, force per charge is newtons per coulomb. So what happens if you take newtons per coulomb and multiply it by coulombs? Then you get newtons, which is force. So if the electric field due to charge Q1 at some location in space is E1, then the Coulomb force, if I brought in some test charge, Q naught, and placed it at that location, the Coulomb force would simply be whatever the electric field is due to charge 1 at that location multiplied by Q naught. And then you would find, because the electric field is force per charge, if I took force per charge and multiplied it by some charge, what I'm getting is force. So an electric field is a hypothetical map of hypothetical forces that might exist at different distances from the presence of a charge. So I want to continue to build on this idea with the idea of electric potential. And so imagine that when you have a charge, and let's say that this charge is, say, positive Q1. And let's say that I have another test charge, Q naught. So let's say we have Q1, we have our test charge Q naught. So the test charge by default is positive. So if we had two positive charges, those charges would want to repel each other. So let's say that, again, I have positive Q1 and let's say I have some test charge Q naught, but let's say that like I intervene and try to make these charges come closer together. Mother Nature doesn't want that. Mother Nature wants these charges to go apart. So what would be happening is that if I was to bring Q naught closer and closer and closer and closer and closer to Q1, what's happening is I would be doing positive work because I would be imparting a force that's going in the direction of the test charge. But it turns out that the Coulomb force, which wants them to go away, is opposite the direction that they're going, which means that the Coulomb force would be doing negative work. And so as this negative work adds up, you have more and more what we call electric potential. And this is a very similar idea to gravity, where with gravity, you have an attractive force between two masses. And so if you have two masses that want to get closer and closer, and you move them further and further apart, then what's happening is gravity is doing negative work. And if you were then to let Mother Nature try to restore things back to the way things were, that means that it would have to do positive work to get things back the way they started. Like, for example, like if I have a mass and I try to lift it higher and higher in the air, gravity is pulling down. So if I'm lifting a mass up while gravity is pointing down, I'm doing positive work on the mass because my force is in the direction of the motion, but gravity is doing negative work. So the more and more I lift it up, the more and more gravity is doing negative work, which means that more and more potential is adding up. And when I say potential, I mean a potential that if I was to at some point let go, then gravity is going to start doing positive work to get things back to where they began, to restore the situation, if you will. The more and more you intervene on a situation, the more and more and more potential is stored to want to get things back eventually if I'm to get out of the way. So you can think of gravitational potential energy as the accumulation of negative work being done by gravity when someone interjects in a situation and lifts, say, a mass upwards. When gravity is doing negative work on that mass, it means there's more and more potential that if I was to let go, gravity would start doing positive work to get it back, to restore it. And so similarly with charges, when you have a charge configuration, if you disturb that charge configuration, Coulomb forces are going to be acting. And so, for example, if I have a positive and negative charge, those two charges want to be attracted towards each other. So let's say that I intervene and start trying to move a charge away when Mother Nature wants those charges to attract. So when I do that, I am doing positive work because my force is in the direction of the motion, but the Coulomb force, so if you can imagine, as I'm moving this away, the Coulomb force is trying to act back. So if the force is opposite the direction, it means that the Coulomb force is doing negative work. And so just like with gravity, if the Coulomb force is doing negative work, it means more and more potential for getting things back to where they originally were if I was to eventually get out of the way. And so it's a very similar concept. And so you can think of electric potential as a charge configuration where there was a certain work required to assemble that charge configuration. And you can think of it as the work per charge. Remember I talked about electric field being the force per charge? Think of the electric potential as the work per charge, which is to say that you can now, just like you can have a hypothetical map of possible Coulomb forces, you can now have a hypothetical map of possible work being done by the Coulomb forces based on the distribution of the charges. So for example, for simplicity, let's just think of two charges. Let's think of a positive and negative charge again. And so we can think of a situation where if I brought some test charge, again, this is that positive Q naught, if I brought that test charge into the situation, what's going to happen? Well, a positive test charge would want to get further away from positive charges and closer to negative charges. So one way you can think of what the potential of a positive charge and a negative charge would create is not unlike, again, the gravity example, where you can think of the positive charge as being, say, a mountain peak, and you can think of the negative charge as being a deep valley, right? So imagine if you had a positive and negative charge, there'd be a peak here and a valley here. And when I mean peak and valley, you can almost think of this potential as like a hypothetical surface where if I then brought in some test charge and dropped it at some location, what's it going to do? So what would happen if you had a potential due to a positive charge and negative charge is if I had like a little test charge and I brought it in and I placed it somewhere, it would want to get away from the positive charge, which would be the gravitational equivalent of rolling down a mountain, right? And it would also, because it's a positive Q naught, want to get closer to the negative charge. So it would roll down into the valley. So in many ways, you can think of potential as this hypothetical map of when you put a test charge at a particular location in this hypothetical potential map, what the work by the Coulomb forces would be done on that particular test charge. So just to review, this really starts with the Coulomb force. You have charges that exhibit forces on each other. Now, you can also think about, well, if I bring a new charge into the situation, what's going to happen? So an electric field allows you to think of a hypothetical map of, given the presence of one charge, and then you bring another charge in at some distance away from it, whatever the electric field is at that point, multiplied by the magnitude of the charge that's brought in, tells you what the Coulomb force between this new charge that was brought in and the original charge that the hypothetical map was drawn about. With potential, now we're talking about work per charge. Electric field is force per charge. Potential is work per charge. So you can imagine that due to Coulomb forces, different charge configurations in nature are going to require different amounts of work to configure them, and different amounts of work that are being done by the Coulomb force. And so think of electric potential as work per charge. And one last time, imagine, say, a positive charge, and imagine a test charge Q naught, and I bring it in from infinity. So since both are positive, if I was actually holding that test charge in my hand, I would actually feel a Coulomb force going the opposite direction, because remember, like charges repel. So if I was to start out at infinity and bring this test charge closer and closer and closer to positive Q1, then what would be happening is this positive charge Q1 would be exerting a Coulomb force in the test charge where the force is opposite the direction that I'm moving it, which means that negative work is being done. And again, just like with gravity, when negative work accumulates, it means that potential energy accumulates, i.e., there is an increasing potential that if I was moving this in from infinity and then decided to let go, well, now the Coulomb force would do positive work, because now the force would be in the direction of motion. And as it does positive work, that potential energy gets converted into kinetic energy. Okay, so when negative work is being done, potential is being stored up, i.e. a potential to restore back to the original configuration. And so as that potential gets more and more stored up, if I was to let go, then that potential energy is more and more going to convert to kinetic energy to get things back to the way they originally were.